bigger, right? Bigger. So positive and bigger, right? And then what happens is I move from my fist to the left. Positive, small, big, what was that? Positive, positive and getting bigger, right? Positive and getting bigger. Positive, but getting bigger. So it should look like that. It's a rough sketch. It doesn't have to be perfect. So in your homework, in the first part of the homework assignment for this section, what they do in the book is they give you a bunch of graphs of f. And then they give you a bunch of derivatives, and you're supposed to match which graph goes with which derivative. That make sense to you? It's like a mix, it's like a matching game. The problem with that is that on the test, you're not playing a matching game. You have to actually draw the derivative from scratch like this. So let's take a look at the review. I don't want to spoil the fun for you, but there are the two problems that I gave on the review for I'm giving you the function and you're supposed to give me the derivatives. On the first problem that I give on the review, can y'all see from this? Let me zoom in on it. Can you all see from this that these are line segments? So this is supposed to be straight line, straight line, straight line, straight line, which is like the first example I gave you here today. That means you know the exact value of the derivative. It's not like, oh, it's positive getting bigger. It's some number, right? So do y'all want to do this? You want to work through it? Do you want to try it real quick? Let me go get a drink. Y'all try this. See if you can do that one. And then if you get that one, do the one below. Just so we're clear, this is one, one unit there. This is 1 unit here. This second one, if you get to the second one, this one, it's curved, so it's going to be approximations. You're going to be approximating the answer. All right, see what you can do. I'll be right back. Any luck? Anybody think they get it? The first one at least? Think you got it? Who else? Yeah? I'm not going to call you out. I'm just curious. 3. That's the first part of the derivative so far. Because what I'm doing, oh wait, sorry, it stops there. There's no arrow there. I apologize. That stops. There's no arrow. So it's only between here and here, the slope of that line segment is 3. Negative 3. God damn it, Robert. I'm having that one of those days. It's negative, isn't it? Yeah. Okay. 1, 2, 3. I'm having one of those days. Negative 3 down here. And then between here and here, what's the slope of that little segment there? It goes up 2 and over 3. So rise over run, 2/3. 2/3, somewhere around there. We're going to have to eyeball that. I'm going to say 2/3 is about right here. So it's going to go like this. And then between here and here, what's the slope? Between here and here, your slope is flat, right? 0? Yeah, 0. So it's going to go like this. And then the last part, we have another negative slope, and it goes down 1, 2, 3, 4, 5. 5, right? And then over 2. So 5 over 2, down 5, negative 5 over 2. Negative 2.5? Yes? So that should be, you understand what I'm doing? Yeah. Okay. Negative 2.5. So we're going to eyeball this right around here. And this one will go forever because there's an arrow down there. Yes? Yes? Oh, on the second one. Okay. Yes?
So when there's straight lines, is it better, is it always going to be like...
Yeah, if your original function are straight line segments, then your derivative will be a bunch of just flat lines with holes at the ends. Or holes when they meet up, right? Like where they come together here.
The circle is closed on the very left side?
Yeah, you can close that because that's closed. All right, now on the second one, do you want to ask your question first?
So whenever you're approaching 0 from the left, is it infinitely getting the slope infinitely?
Very, very good question. Okay, let me address that after I knock out some other things on it first. So do you all agree that right here, and then on this little segment right here, the derivative is 0? So my derivative should be, here it should be 0, and then between here and here it should also be 0. Right? I'm going to do that. And I'm going to leave this open for right now, just because I'm not quite sure what's happening otherwise. Like at the actual end, I'm not going to worry about it, and here I'm not going to worry about it. Let's do this right side. What happens if you look at the slope of the tangent line over here? Here it's 0, right? Like right at that point at the top, it's 0. And then it starts to become what? Negative and bigger negative. So it should just go like that, right? Those are negative values, and they get bigger negative. And because at this point the tangent line actually exists there, I can fill this in with a solid dot.
So when it's 0, when should we put it closed and circled?
If you have a corner like that, do not put closed. Leave it open, all right? Or if we have a jump in the graph, which we haven't done yet.
Going from a 0 slope to a negative slope?
It's a slow, gradual process, isn't it? If I'm at this point, what happens? I start to slowly become negative, right? So it's just this slow, gradual process. As opposed to if this were a straight line segment, then it would be an instant change. We would go from flat to all of a sudden being on a line. See the difference?
So like on the other side, it's a sharp curve.
Yeah, so I'm going to leave this till the very end because this is the hardest part of the whole thing. Let's do this part here. What's happening? Let's start at the bottom. My derivative is 0, and then what? As I move this way, those are what? Small negatives, and they're getting bigger negatives. So it should look like this. Small negatives getting bigger negative. Yeah? Yes? Okay, so tell me, I'm going to start here, and what's happening?
It's getting bigger
Positive, positive, right? What happens here?
It's non-zero
The, so the question was originally, in my picture, does it look to you like this is like the problem I did before where we had this? Does it look like this scenario where it's becoming vertical to you? You don't think it looks vertical? I didn't draw it so that, I didn't draw it in, how do I say this? I did not mean for it to look vertical when I drew it, all right? For me, it was supposed to come in, it's like the slope is it's positive getting bigger, positive getting bigger, positive getting bigger, and then it just stops, right? So that means it's like positive getting bigger, positive getting bigger, positive getting bigger, and then just stops. And from there, once you get to that corner, you're going to jump to 0 and just continue. Now, had I wanted it to become infinite, here's how I would have drawn that one piece. I would have done this. So here's that point at the top coming straight over and then curving like that. If I wanted that to look vertical, here's what I would have done. I would have come in and I would have come in like this. Something like that. Do you see the difference between those two? That's more like, hey, look what's happening. Positive getting bigger, 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 and then it's trying to become vertical, right? All right, so those are on the review, just to give you an idea.
So how would you draw the derivative on
Of which one?
that?
The difference here, so let's just say that that's what this one did, right? The only difference in my picture would be this.
Would it just go to the vertical?
It would be like a vertical asymptote like that. Now on the test, I'm not going to try and confuse you with something like that. The picture on the test, I don't think there's going to be any sort of gray area. It'll be, because I'm more testing the idea, I'm not trying to like push, because this is almost drawn in a way that I'm trying to get you to think about which one of those it is.
And we are going to have like the grid, right? Like you are just...
Yeah, I'll make sure that you know where everything is, yes. Like you'll be able to calculate these slopes. Yeah. All right. So what we've done, all right, in what, hour and 20 minutes, is that we've said, hey, if we have a function, right, we can do this thing called taking its derivative, and it creates a new function, and we can look at it visually, right? We can see, if we start with the graph of the original function, we can actually come up with the derivatives picture. Let's move on in the notes. I don't want to go off on a tangent here. So here are some more examples that are in the notes. So I'm just going to run through these very quickly for you. Here's the original function, right? Let's move across this function and talk about its derivative. So what would the derivative be right about there? 0, right? Right about, I don't know, it's hard to see it. Right around there, right? The derivative there is 0. So that would be the point that corresponds to the derivative there, right? And as I move to the right, what should happen? The derivative should become what? Positive, bigger and bigger until it gets to about right here, and then still positive, but
it
goes back to 0. So the point should get bigger and bigger, and then it should go back and go back to 0. And then it's going to be small negatives getting bigger, and then eventually it's got to get back to 0, right? So that's, the green is basically representing the derivative, and I should have put the line there. Here, let's just draw it together. So there it is, goes up, comes back down, kind of maxes out on the negative, and then goes back. Okay? What about that derivative? What's the slope of this line? 3. So when I move across, I should just have a constant derivative, right? 3.
Because the slope is 1.
No, the slope is 3 because the function is 3x.
But because it's not. Yes.
This slope is 3. It's hard to see, but this slope is 3, which means the derivative should always be 3. Okay, now we're moving on. We're done with pictures. It's time to move on and talk more about this whole idea of starting with a function and getting a new function. And it turns out that we have a lot of different notations that mean exactly the same thing. So this f prime of x, we all understand, is the limit, right, that we talked about at the beginning of class. I'm going to put it on the board over here on the side. This new thing, f prime of x, is the limit, and we're using the second definition, f of x plus h minus f of x all over h. That's the second definition from last class, replacing the a with x. And we realize that that gives us a new function. This is such an important new function in math that we have different notations for it. So if you're given y as a function of x, if you see f prime of x, it means that. But if you see y prime just by itself, y prime, it means, hey, go do that limit. If you see dy over dx, that means, hey, go do that limit. If you see df over dx, it means, hey, go do that limit. These all mean the same exact thing. If you see d over dx, this says, hey, take the derivative, treating x like your variable, and take the derivative of the function f of x. This also means take the derivative of that function. This also means take the derivative of that function, treating x like your independent variable. All those notations are exactly the same. The ones that we will use in this class are this one, this one, this one, and that one. Those are the 3 that we're going to use almost exclusively. You don't really see this. You don't really see that much at all. But this one you won't see until you get past Cal 2. In Cal 3, we have to do something else because we have more than one variable in Cal 3. So I don't know if you all know how calculus, the sequence, works. In Cal 1, everything is about derivatives. I mean, the whole class has to do with differentiation, taking derivatives. Cal 2, we basically do that same operation backwards. So it's like instead of going from here to here, Cal 2 is about going from here backwards. Extremely hard to do. Okay? And then Cal 3 is you take everything that we've done that used to just be functions on flat sheets of paper, and we talk about functions that live in higher dimensional space. And then you just do all the calculus you learned in 1 and 2, but in higher dimensional space. So in Cal 3, we're going to have variables like x, y, z. You could have other variables as well. So we have to be very specific or very explicit about what variable we're talking about, which is why this notation is used. Okay. I told you all before at the first day of class that calculus came from 2 different people, right? I told you all that? Newton and Leibniz were the 2 fathers of calculus. They developed it on their own, right? I did tell you all that? Yes? Okay. So the reason we have different notations is because Newton used his own notation. I mean, he was making this up, right? Not making it up, but he was trying to figure these things out. So he used his own notation. And then Leibniz, since they didn't know each other and weren't working together, was using his own notation. So we have different notations, all right? This notation right here is called Leibniz notation. And sometimes Newton's notation is better. Sometimes Leibniz notation is better. There's usually an argument in the math world about who's better, right? Newton or Leibniz when it comes to calculus. And it's not a very big debate because Newton had something that Leibniz didn't have. Leibniz didn't go as far as Newton did with the calculus. Newton developed something called series, and he could do problems that Leibniz couldn't do. So like where Leibniz had hit some roadblocks and couldn't figure it out, Newton had created a new tool that allowed him to do those. So a lot of people think Newton's version was better.
Are they both German?
No, I don't know. I don't know backgrounds on them exactly. Yeah, sorry. I don't know if Leibniz. It looks German. I don't know. I'm not going to. There is a debate also right now. There are some people who believe that Leibniz stole Newton's stuff. That somehow Leibniz got his hand on Newton's materials and cheated. But we're not going to settle that here today. All right. They're both gone, long gone. So we may never know. All right, this next part has to do with just language. All right, so new terminology. A function f is said to be differentiable at some value a if the derivative at that value a exists. Remember, the derivative is a limit, right? So as long as the derivative exists, right, as long as the limit exists, then we will say that the function is differentiable at that point. So when we talk about differentiability, we're talking about some function at some point a. Does the slope of the tangent line, does that limit exist? Do we have a slope? Now, if your function is differentiable on an interval, so let's say we take an interval, let's say we go from a to b, let's call that interval I. Okay, so all the points between a and b. To say that a function is differentiable on an open interval I is to say that at every point in here the derivative exists. So it's a stronger condition to say something is differentiable on an interval because that means it's differentiable at every point in there, as opposed to the top one, which means just differentiable at one point. Now we have a theorem. This theorem says that if your derivative exists at a point, so if your function is differentiable at some point, that means the slope of the tangent line exists, then your function must be continuous there. Do you remember what continuity meant? It meant you could draw without picking up your pencil. If you tell me that the derivative exists at some point, then I can guarantee you that at that point, the function comes in from both sides to the same point, and the whole is filled in. That's what continuity was. From both sides headed to the same place, and that point in the middle is filled in. It's impossible for you to have a derivative exist, but then not have continuity at that point. That's what this theorem says. And then I say, be careful, because when you read a theorem, you have to be careful how you read it. Has anyone here taken any logic courses? Any logic? Yes, you have? Have you seen truth tables and stuff? Yeah? Okay. So I'm not going to get into logic too deep, but I do want to talk briefly about the way theorems work. When you have a theorem, there's usually an if statement and then a then statement. So it's like, if this is true, then this is the result. So we usually notate those as if P, then Q. So for our statement, our P statement is this, P. Then the conclusion is Q, right? So this is saying if the function is differentiable at a point, that slope of the tangent line exists, then you've got continuity at that point. So you read it if P, then Q. This down here where I say careful is saying you have to be careful with if-then statements. You can't just reverse them. Okay? You cannot just say, oh, if it's continuous, then that means it has to be differentiable. Theorems don't work that way. And the best example I can give you of this to make you hopefully understand is this. If I tell you that you are standing in Texas, right? Then do you agree that you're standing in the United States? Like if I'm standing in Texas, then am I standing in the United States? Yes, right? Does it work the other way around? No. If you're standing in the United States, then are you standing in Texas? Could you be? Yes, but do you have to be? No. So see, I can't just reverse these. And that's what this theorem is saying, is that if this is true, then that's true, but it's not necessarily true the other way around. All right? So differentiability implies continuity. That's what this theorem is called. Differentiability implies that we have to have continuity. So the natural question becomes, when do functions fail to be differentiable, right? If I give you a function What would make it not be differentiable? What would give us a problem where we couldn't find the slope of a tangent line? And we've already seen some of these. There are 3 different scenarios that can happen. We either have a corner or a cusp, a jump in the graph, or a vertical tangent. And I'm going to show you a picture of each of these 3. Right there, that function fails to be differentiable where? At what x value does it? It fails to be differentiable at 0. The derivative does not exist at 0 because what's happening is the derivative goes from what? Positive to immediate switch over to negative. So if I were to graph this derivative, well, I can have the computer do it. Here's the derivative. I'm going to have the computer graph it. It's positive derivative, right? And then immediately flips over to negative, right? So it goes here and then down. So at 0 we have our derivative is undefined, right? Our derivative fails to exist. That's going to happen at a corner or something called a cusp. So that's a corner. Let me show you what a cusp looks like. That's a cusp. It's like 2 curves coming together into a point. And I hope you can see that if you try the derivative here, it's what? Positive, 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 positive. And then all of a sudden, flips over. Shit. Falls off the, right? Rolls. Someone trips. You all right? Yes? And then it goes from positive. There's no slow, gradual turning. It's just an instant flip. And so that would fail to be differentiable. So corner or cusp. Anytime you have a jump in the graph. If your graph breaks, then at that point you can't have a derivative. Why? I want to give you an example. Okay, good. Because it's not what? Not continuous. Look, I'll give you a better example than that one. Look at this one right here. What if I draw a line that goes like this? And let me tell you that the slope of that line is 1. Okay? Then what would the derivative of this be? Anywhere over here. What would it be? 1, right? Okay, now what I'm going to do is I'm going to make a jump in the graph, and now I'm going to continue that line with the same slope. So what's the derivative over here? 1. What's the derivative over here? 1. So the derivative would be 1 the whole time, right? Yeah. But when you get here, you have a break in the graph, don't you? Yeah. But we said, the theorem said that differentiability implies continuity, right? So I cannot say that this is differentiable here. Let's call this point A. I cannot say that I'm differentiable at A because that would mean that I'm continuous at A, and this is not continuous at A. So anywhere you have a break in the graph or a jump in the graph, you will fail to be differentiable at that point. So corners and cusps are your first group where you would have you would fail to be differentiable. Anytime you have a jump in the graph, at the point that you have the jump, you would fail to be differentiable. And then the last one is the vertical tangent, which we looked at this one. I drew this on the board, right? We drew that graph, and then when we drew its derivative, it looked like this, right? That's what the derivative looked like because it was trying to become vertical. And so that was a vertical asymptote. So at 0, we fail to have a derivative. This right here, this point right here where we're getting this problem, we call this a vertical tangent line. See, the tangent line is trying to become vertical, isn't it? Tangent line is trying to become vertical. We know that vertical tangent lines, the slope of vertical tangent line, or slope of vertical line is undefined. So my derivative cannot exist at that black point right there. And that's it. Those are the only places where functions will fail to be differentiable. Corners, cusps, jumps, vertical tangents.
Would holes be the same thing as a
Pardon?
What holes be the same thing as a jump?
A hole would be discontinuity, wouldn't it? So if you had discontinuity, then you couldn't be differentiable there. All right. So mathematicians are weird people, all right? I can say that because I'm a math person. The theorem that I gave you a minute ago said that if you're differentiable, you have to be continuous somewhere, right? Mathematicians asked this question. They said, well, I wonder if there's a function that is continuous everywhere. That means you can draw it without picking up your pencil, but nowhere does the derivative doesn't exist anywhere. Like, for example, this function right here, is that function continuous everywhere? Continuous. Can I draw it without picking up my pencil? Yes? Okay, so I'll put arrows. That is a continuous function. Is it differentiable everywhere? No. Where is it not differentiable? At the peak, right? So mathematicians said, is there a function that is continuous everywhere, but nowhere differentiable? Meaning there's no point on the graph that has a derivative. See, there's a bunch of places here where the derivative exists, right? Except up there. But everywhere else it does. So, that was the question. The question, we ask questions like that in math not because it matters, like, oh, well, it'll be great if we find this function. It's just more like, I wonder if one exists, right? So I want you to imagine this function. We actually found it, okay? Mathematicians found it. This guy named Weierstrass, all right? He found this function, and here's the idea behind the function. Imagine a function that looks like this. Okay, is that continuous everywhere? Yes? Okay. Is it differentiable everywhere? No, there's some places where I have problems, right? Every one of these peaks, every one of these corners, I would fail to be differentiable. But I'm still continuous here and differentiable, right? I'm differentiable in all these other places, right? So instead of drawing it like that, let me draw it like this. So what I've created is now, it's like, think of these as like a saw blade, the teeth on a saw blade. And imagine that each tooth of the saw blade actually is a bunch of teeth of another saw blade, right? And then if you zoom in on any of those little teeth, it's a bunch of teeth again. And if you zoom in on any of those, it's a bunch of teeth again. Do you get the idea? Okay, so Weierstrass actually came up with a function that does this. Okay, and I'm going to show you the function right now. This is what it looks like. A computer has a hard time graphing it because of all the crazy shit going on in it, all right? Let me see what I can do here. If I try and zoom in on this, see, the computer's having a hard time. Yeah, the computer's having a really hard time. Let's do this instead. Let's go and do Weierstrass function. Let's just look it up. It's probably a better graph right there. There it is.